Okay, thank you very much for the invitation. And I have given talks on these topics for a couple of times, but on more technical stuff. So today I try to give more examples and say a little bit about motivations. Okay, so I hope this will be okay for you. This is a joint work with Polychuk. So let me start by recall the notion of Poisson algebra. So can you see what when I write? Okay, so this is
a white color.
Yeah, so I need to change color. Okay, so let me start with the commutative algebra over C. Okay, and by a Poisson algebra means we have a Lie bracket. Satisfy the three well-known conditions. First one is skew symmetric. Second one is you want the bracket acts as a biderivation. Finally, it's Jacobi identity. So here the upper index cyclic means I permute ABC cyclic. Okay, so I get 0. So the basic example, or the first example, is the polynomial algebra. So if we let A to be the polynomial algebra, say of m plus 1 variable, and then a Poisson bracket defines you this binary operations. But let me just assume this algebra or this bracket is homogeneous of degree 2, which means I'm going to get a quadratic polynomial. So here it's n. Okay, so there is a special reason why I care most about the quadratic Poisson bracket, which will become clear later. So of course, these coefficients are not arbitrary. There are two obvious conditions, which is this one from the skew symmetry, the other one coming from the commutativity. Okay, so but the non-trivial condition really comes from the Jacobi identity. So the Jacobi, so this one is called, sorry. So this one is called the Jacobi identity. So this one, this will give you so the Jacobi will give you some quadratic equations. Okay, so let me just write down the answer. I'm use the Einstein notation. So I do the cyclic permutation. So this is some quadratic equation satisfied by this coefficient. And you will see that, I mean, to classify Poisson bracket is essentially classify this variety given by this quadratic equation, modular isomorphisms. Okay, so in general, this is a very complicated question. Even we restrict to quadratic algebra, still very complicated questions. This variety will have many components, and it's not clear what is the right invariant or the effective invariant to classify it. But let me just point out one consequence, also the reason why I consider quadratic Poisson algebra. So if I consider the quadratic bracket, then it induces a Poisson structure on another polynomial ring, which is given by the homogeneous, by the dehomogenizations. Okay, so I pick a k from 0 to n, and then I dehomogenize the polynomial. I divide by, let's like the way we write down the local coordinates on Pn. So we dehomogenize it. I claim that the bracket that I defined previously indeed defines a Poisson bracket on this polynomial. Okay, so this is an easy calculations. If I try to define the bracket on this new polynomial ring, I just force the Leibniz rule holds for the rational function, so which means I'm going to make the following definition. Okay, so this is like force the Leibniz rule holds for the rational function. But if I further expand it by further apply Leibniz rule, I'm going to get the following final formula, which has 3 terms. Okay, but now you see that quadratic condition plays a role since the original bracket is quadratic. Then this final formula makes sense on this rings, right? Because it's homogeneous of degree 0. So therefore, it's easy to check. Indeed, it defines a Poisson bracket on this ring. So this is where the quadratic is used. You want it, the answer, the result is homogeneous of degree 0. Okay, so I mean, later when I introduce the geometric definition of Poisson structure, you'll see this exactly says that a quadratic bracket on the polynomial ring will define a Poisson structure on the homogenizations, i.e. the projective space of dimension n. Okay, so now let me introduce, recall the notion of Poisson manifold. So I'm going to start with a complex manifold. So I'm going to only focus on complex Poisson structure today. So it is a Poisson manifold if the sheaf of functions OM is a sheaf of Poisson algebra. Okay, so this definition has a variation or equivalent way to state is using so-called bivector. So I'm going to consider a O linear map from the cotangent bundle to tangent bundle, satisfy the following condition: pi dual is equal to minus pi, it's skew symmetry. And if I have a Poisson manifold defined the way that OM is a Poisson algebra, sheaf of Poisson algebra, then I can define this bivector using the following formula. Okay, so this is obviously satisfies skew symmetry, but you can actually verify that this pi is a bivector. So why it is called bivector? Because it's skew symmetric. So this belongs to wedge 2 of Tm. So this is called a bivector. Indeed, satisfy so-called Skelton bracket conditions. Okay, so let me now quickly recall what is a Skelton bracket. So remember that the tangent bundle with respect to the Lie bracket of vector field is a Lie algebra. So now I can define, so take xi vector fields, then I can define a new bracket on wedge of vector field. Okay. So this one I defined it, I denoted by SC for the Skelton bracket. So let me write down the definition. So this one is x1, wedge x2. So sorry, let me write down the final answer. x1, x3, x2, x4 plus x1, wedge x2, x3, x4 minus x3, x1, x4, wedge x2 minus x3, x1, wedge x3, x4. Okay, so the brackets on the right hand side is really the Lie bracket on the vector field. So I define kind of a new bracket on wedge 2 of Tm. So the output will be a wedge 3 of Tm. So this is called the Skelton bracket. Actually, this one really extends to the whole polyvector field for all P. Okay. But then the dimension, to write down the general formula, you have to have some sign depending on the degree of the polyvector field. Okay. But I only need this degree 2 part to define my integrability conditions. Okay, so indeed, together with wedge, this defines a -1 shifted Poisson algebra structure on the space of polyvector field. Okay. Or another name for that is the Gernston-Hubbard algebra structure. Okay, so under this new structure, you can easily translate the Jacobi identity, which is the most non-trivial part of the Poisson algebra axiom, to a integrability condition about Pauli vector field. So the Jacobi identity on OM is then equivalent to the condition that pi and pi bracket equal to 0. Okay, so the advantage of this new definition is a kind of base. It does not depend on the base, and it's more easy to check geometrically. Okay, so let me start with one example. So a Poisson structure, according to the previous definition, on a projective space of dimension n is a section of T wedge 2, okay, such that it's a section pi here such that this is equal to 0. Okay, so now we can look at this remark here. So what I really verify here is that a quadratic bracket on Cm plus 1 will give you a Poisson structure of Pn, which is the projectivization of Cm plus 1. Okay, so this is obviously uniquely defined just by this formula here. Okay, so but actually the opposite is also true. So if given a Poisson structure on Pn, you can always lift it to a quadratic bracket. So the lift always exists, but not unique. For this, you have to show something. Okay, it's not completely obvious. Okay, so this gives you the correspondence between Poisson structure on the projective space, which is compact, and a bracket on Cm plus 1, which is completely algebraic. Okay, so now let me state a kind of more nonlinear example of Poisson manifold. So let S be a projective smooth surface. Okay, so with negative anti-canonical class. Negative canonical class. Okay, so the canonical bundle is negative. So in this case, because it's a surface, we can take an arbitrary section of the anti-canonical line bundle. In this case, it's ample. Okay, so let me assume there is a non-zero section, but even though the section is 0, still makes sense. Okay, so this defines a Poisson structure on the surface S. So you may wonder why we don't need to check Jacobi identity, because in this case, Jacobi identity is trivial, okay, since it's a surface. So Jacobi is trivial. We don't need to do anything. Okay. For the threefold, then it's non-trivial. Okay, so because the surface, wedge 3 automatically vanish. Okay, so this is not the example that I want to give because this is so trivial. So instead, I want to take the moduli space. So let S upper n to be the Hilbert scheme of m points on the surface S. Okay, so or alternatively, an object here will be a Z is a 0-dimensional subscheme of S with degree n. Okay, so I want to make this moduli space. So this is obviously a smooth projective manifold of dimension 2n. Okay. And usually the topology of that is much more complicated than S itself, even though it's determined by S. Okay, so yeah, any questions? Okay, so I want to define a Poisson structure on this moduli space. So first, note that the tangent space of the Hilbert scheme at the point Z or the subscheme Z can be identified with the first extension group of the ideal sheaf of IZ. Okay, and alternatively, the cotangent space is the dual of that, i.e., extension of ideal sheaf with by ideal shift twist by the canonical bond, by cell duality. Okay. So a bivector will be a map from the right to the left, which satisfies the skew symmetry and the Jacobi identity. Okay. So there's an obvious map given by pi, which is just the multiply by the section of the anti-canonical line bundle. Okay. So this is just the multiply this element. Okay. Okay. So it turns out that this is a Poisson structure. Okay. So, however, in this case, rather than the surface itself, the Jacobi identity is non-trivial to check. Okay, so this is enough. Okay, so this, of course, is a generalization of Mukai's construction of the symplectic structure on the moduli space on K3 surfaces. Okay. Instead, we take a section which is of the anti-canonical bundle. So to construct this bivector. So this will specialize to the K3 surface cases if omega s is trivializable. Okay. So let me now make a definition to link to the symplectic geometry. So a Poisson bivector is called non-degenerate if this map pi from omega m to Tm is invertible. So in this case, we can take the inverse. This is a 2 form. Symplectic form, actually. It's a symplectic form. Okay, so here the Jacobi identity will translate to the closeness of the form, and non-degenerate, of course, correspond to the non-degenerate of the 2 form. Okay, so these are basic definitions. Let me give some heuristic. This is not the theorem, but rather like a heuristic. So any Poisson manifold can be embedded into as a Lagrangian into something called one-shifted symplectic space. Okay, so here I didn't define what is one-shifted, what is the space here, okay, and what does this mean by Lagrangian, okay. But anyway, the heuristic, I will give you some explanation, which in a very vague sense, but really in the infinitesimal level. So say if you have a vector space V, which is your tangent space for your Poisson manifold, right? So what is the bivector? The bivector should be a map from V star to V, right? So you imagine this map, linear map, as your bivector, okay? So, but what do I mean by any Poisson manifold can be embedded into, as a Lagrangian into something which is one-shifted symplectic, okay? So let me just make out of this a short exact sequence or exact triangle. So this, you can view it as just some exact sequence of vector spaces, okay? So I put V plus V dual, but shift by 1. You view this as your, how to say, tangent space of your symplectic space, which is one-shifted. So this one-shifted corresponds to this shift here, okay? So the left-hand side here, you get an exact triangle, okay? And this map here is Lagrangian in the shifted sense, and this structure here is one-shifted symplectic. As I said, infinitesimally, okay? So there's a pairing, but it's a perfect pairing, but with one shift. Okay. So by exactness, you see that this map here is determined by the exact triangle, right? So therefore, determined by the first map being Lagrangian. So we have a Lagrangian map from V to V plus V dual shift by 1, okay, which determine the mapping cone of that determines this map here, which is our pi. Okay, so in the heuristic sense, to determine a Poisson manifold, or any Poisson manifold will determine such a symplectic space together with a Lagrangian morphism. Okay, so I'm going to make this slightly more precise in the follow-up examples. Okay. Okay. So now let me be more precise. So first, I define term Calabi-Yau curve. So a connected projective curve, not necessarily smooth, C, with trivializable canonical line bundle is called a Calabi-Yau curve, okay, or Gorenstein-Calabi curve. So omega C should be a line bundle, should be invertible sheaf, and moreover, it's trivialized. Okay, so let me give some simple examples. Of course, elliptic curve is the first example, and you can have a nodal curve. Okay, so this means plane cubic nodal curve, and you have a cuspidal curve, also degree 3. Also, you can have something which is not irreducible, for example, the so-called EM fiber of a Kodarias classifications, something like this. So this is E3. You can have more. Okay, so like any curve in the Kodaria Enrique classification of the degeneration of the curve will be such an example. Okay, so another term is called perfect complex. So if we have X is quasi-projective, a complex of quasi-coherent sheaf. So this is a complex of quasi-coherent sheaves. So it's called perfect if it is quasi-isomorphic to a bounded complex of vector bundles. Okay, so this is standard terminology. So I denote this stack or category of perfect complexes by perf X. Okay, so this contains some interesting substacks. One of them is called so-called graded vector bundles, and the smaller one is the usual vector bundle. Okay. So by graded vector bundle, I mean it's a complex, but with degenerate differentials. So all V are vector bundles, but the maps are 0. Okay. So this is, of course, a perfect complex, but I call such complex graded vector bundles because the differential has no information. Just only remember the grading shift. Okay. So and if I just put everything in degree 0, then we get the usual vector bundle stack. Okay, so these are some open substacks. So now let me recall a fundamental theorem of Pantiff-Tohen, Vacchi, and Lisossi. So now let's see be Gorenstein-Calabi-Yau according to my previous definition. So then the stack of perfect complex on C admits a one-shifted symplectic structure. Okay, so let me just remark that if C is smooth, like an elliptic curve, then you don't have to distinguish perfect complex and coherent sheaves. They are the stacks, they are equivalent. But for the singular things, you see, you actually do make some selections on the singular curves. Some coherent sheaves, they're not perfect. Okay, so this will be a problem if you want to consider compactifications. And however, for the defining the Poisson structure, this is very important that we do want to exclude those things which are not perfect. Okay, so this is just a remark. For elliptic curve, for example, this doesn't really matter. Okay, okay. So yeah, any questions? Okay, so instead of giving you a formal definition of shifted symplectic structure, I want to just describe the idea behind these definitions. Okay, so again, I look at.
Pardon? So when you say one shifted symplectic structure, you mean the morphisms space has linear one shifted symplectic structure? When you say a category has a one shifted symplectic structure, meaning?
No, this is stack. Sorry, this is a stack.
Oh, okay, I see. Okay.
Stack of perfect.
So this. Okay.
Sorry. Okay. So, yeah, sometimes we use the same notation to denote the category, but here it's the stacks, yeah, not the category. Okay. So again, I try to describe this symplectic structure in the infinitesimal level. Okay, so the tangent space or tangent complex of perf C will have several components, but let me focus just on. Let me specialize to vect, since this case is probably the most interesting case. In this case, we have the tangent. Now it's not a tangent space, but because this is a stack, so it's a tangent complex. It contains.
冰箱那个不要得是买给你吃的，你怎么都没喝？
Any questions?
我上一瓶才刚喝完。
哦，我没有注意到你都没喝，所以我又买了一罐，现在冰箱有2罐。
我没差。
Any questions? Hello? Hello?
I think you can continue.
Please continue.
Okay. So yeah. So let's E be a vector bundle. Then we have x1. This is my tangent space, and we have. But this is what I should really write tangent 0's tangent space, and we have x0, which is my -1 tangent space. Okay. So these are all the tangent components for the vector bundles. Okay. So and remember, a symplectic form means you need to have a map from tangent to cotangent. So the map is exactly given by the so-called cell duality map. So first I take the Calabi-Yau structure, right? And then I apply the cell duality. Okay, same thing for the other one. Okay. So this is an isomorphism because OC is invertible. Sorry, it's trivializable. Okay. So this is nothing but T-1 dual, right? And this is T0 dual. Okay, so you see that instead of having T dual with omega, so sorry, we get a isomorphism from T to omega, which is a 2 form. We get a T maps to shift of omega, or vice versa, or shift of T maps to omega, right? So this shift is exactly 1, right? Because you send 0 to the -1 piece, or really the 1 piece if you use the grading for omega. Okay, so this is why it's 1 shifted. Okay, so this is like in the cohomology level, right? Infinitesimal and the cohomology level. Okay, so the hard part to prove this theorem is to make the right definition of, or the globalization of this structure. So let me just comment that the hard part, the two parts. Okay, first is to define the right notion of closeness. So remember, to construct the symplectic structure on a moduli space, the most difficult part is to check the closeness, not to check the non-degenerateness. Okay, non-degenerate is like something you can check point-wise, but closeness requires local calculations, which is really the hard part. First hard part. Second hard part is to make the definition a homotopy invariant. So there are some attempts before PTVV on generalize this Poisson or symplectic structure of Mukai beyond the smooth part of the moduli state. And I think the failure is due to the fact like the definition does not work well when you want to define morphisms, like you want to make it functorial. So the PTVV is probably they succeed because they find a functorial definition. Okay? So I'm not going to give the definition, but I think this gives you some intuition that what should be the like classical shadow of this shifted symplectic structure. Okay, so so now let me quickly remind you the important notion in Poisson geometry, the symplectic leaf. So let M pi be a Poisson manifold. Pi is a bivector. Then there exists a foliation M, which is disjoint union of some submanifold. So these are submanifold, but not necessarily open or closed. Okay, so it could be just locally closed, such that if I restrict myself, the Poisson bivector to this slice or this strata, we have it's non-degenerate. Okay. So such M lambda will be called a symplectic leaf. As I point out, if you have a non-degenerate Poisson bivector, then you can invert it to define a non-degenerate closed two form, therefore make it symplectic. Okay. So let me just remark that in general, this index set lambda may not be finite. Moreover, even though M is algebraic, it does not imply M lambda is algebraic. Okay, so if you have M is symplectic to start with, then there is only one strata. Okay. I'm assuming, okay, so there are some technical assumptions about connectedness, but let me ignore that in this talk. So usually you need to take the connected component, okay, to be a symplectic leaf. Okay. But if M is connected and symplectic, then there is only one strata. Okay, so let me give one example of a symplectic leaf. So let's take pi to be a anti-canonical section of P2. Okay, so in this case, we know omega P2 is just O3. So therefore, the zero locus of this section will be a cubic plane curve. Okay, so in this case, it's easy to check because the dimension is 2. The complement of this cubic is a 2-dimensional leaf. Okay, and i.e. rank of pi restrict on this any point is equal to 2. Okay. Moreover, if I take a point inside the zero locus of the section, then this is a 0-dimensional leaf. In other words, the rank is equal to 0. Okay, so this is a relatively trivial example, but let me now give a less trivial example. I take P2, but take the Hilbert scheme of 2 points. Okay, so in this case, let me just give some examples. So now dimension is equal to 2. As I point out in the previous example, right here. So yes, right. P2 itself, if you choose a anti-canonical section, they give you a Poisson structure, but the Hilbert scheme of points will inherit a Poisson structure defined in the following way. Okay, so now if I take this Poisson structure, I will give you some example of this symplectic leaf of this 4-dimensional space. So this has dimension 4. So first, there is exactly one 4-dimensional leaf, which is just the Hilbert scheme of the complement. So note that this one is not going to be affine, right? Even though the complement of Z pi is affine, but the Hilbert scheme of 2 points is not affine. It contains some compact submanifold. Okay, so this is symplectic. Let me give another example of 2-dimensional leaf. So I'm going to consider points P1, P2, such that P2 is fixed and lies in Z pi, and P1 belongs to the complement. Okay. So the subscheme correspond to these 2 points, give you a 2-dimensional submanifold, because P1 can vary, right? You can vary this, and this is a two-dimensional leaf. Okay, if this second point is fixed, sorry. Okay, now let me give an example of 0-dimensional leaf. I take some point P lies in the regular part of the zero locus. Okay, I'm not assuming Z pi is smooth. Okay, if smooth, then any point is okay. So now I can take the double point. Okay. So this gives me the example of 0-dimensional leaf. Okay. Okay. So, but if you try to classify all leaves, then you see immediately there is a problem that to classify them, you see that the first one is that's a unique leaf, but there are many 2-dimensional leaves and there are many 0-dimensional leaves. And okay, so we have to make it precise. What do we mean by classify? Is it just set theoretical, or usually when in algebraic geometry, we expect to have some notion of invariance, discrete, and continuous, right? So the question. Yeah.
So when you say 2p, you mean that p together with the direction along this zero cycle, right?
Yeah. So because it's on the curve, so this
on
is
a curve only, right? Okay.
Yeah, unique. So that's why.
But if you look at those vectors along the other direction, they form a two-dimensional leaf or what? They are inside two-dimensional leaf.
Yeah, these are not the same zero-dimensional leaf. I mean, if you look at other directions, yeah. So
yeah.
they are not they belong to the two-dimensional leaves. Yes.
They do. So
okay. I'm not saying these are the all leaves. These are some leaves. To really classify them, it's a very complicated question. I'm going to give a partial answer later. Yeah. So you will see that to just look at the geometry, like whether the tangent vector point to certain directions, is not a very effective way to classify leaves, especially when the n goes big. It just this method. There's no way you can classify in this way. But later I will see how to solve this problem. Okay. We will see. Okay. So but this is a general question. If you're given a Poisson manifold, how do you classify leaves? So the usual philosophy in algebraic geometry is we look for some discrete invariants, right? And we look for some continuous families, okay? Or continuous families. Okay. So the usual idea is the discrete invariant, for example, there is an immediate one for Poisson structure that is the rank of pi, right? So you look at those point pi's, such points on the manifold such that rank of pi is fixed, right? That's the obvious discrete invariant. But this is clearly too rough. It doesn't give you a good moduli space. Okay, so we need something more refined. Okay, what is that? It's not clear. Okay, but we expect to have discrete invariance so that it's finite. We don't want this discrete invariant can take infinitely many possible values because my manifold itself is bounded, right? So I expect the discrete invariant which correspond to certain stratification, which is finite. Okay, so this is very important. Okay, so given a discrete invariant, then we can talk about continuous family, i.e., moduli space of leaves with fixed discrete invariant. Okay, so this is a type of the philosophy in algebraic geometry. Okay, okay. So I will try to at least give some example where this will work out. Okay, so let's recall that in the heuristic, we have for any Poisson manifold, I'm going to have some Lagrangian morphism to something which is symplectic. Well, this is one shift is symplectic. Okay, so it turns out that the question or the problem of classification of leaves is closely related to the geometry of this space X, which I didn't really define, and it may not exist. Okay, so this symplectic space. Okay, so let me justify using the examples. Okay, so now let me define my main moduli space. Again, C should be a Gorenstein-Calabi-Yau curve, and I denote by complex C the moduli space, moduli stack of bounded complexes of vector bundles. Okay, so you may wonder what is why we use a new terminology since we already have perf. Well, okay, so the object is the same, but for this new moduli space, I use a different set of isomorphs. So here, equivalence is really defined to be the chain isomorphs. So what does mean by two such complex being isomorphic? It's just in the most rigid way, I want to have a vector bundle isomorphism termwise, which commutes with differential. Okay, so this is my notion of equivalence. Okay, obviously this is much more rigid than quasi-isomorphism, right? Quasi-isomorphism means you don't require this to be isomorphism, it just means a chain map so that induce isomorphism on cohomologies, right? So that's a much weaker condition. Okay, so we have this, and this obviously makes this a stack. Okay, and we have two obvious maps from this stack to two known stack. First one is graded vector bundle. Second one is perf. Okay, right. So the map is fairly obvious. We just send by P to, you just degenerate all the map to 0. Okay, so here it's not 0, but yeah, degenerate to 0. This is the first map, P map. And for the second map Q, I send it to the underlying perfect complex. Okay, that just means I consider this up to quasi-isomorphism. Okay, something like you mod out a bigger equivalence relation, okay? or I should say coarser equivalence relation. Okay, so these are the two stack maps from complex C to graded vector bundle and to perfect complex. Okay, okay. So these are
Huazhang,
yes.
If you change D to 2D, are they equivalent in your sense?
What D? What D? Sorry.
D is this the map, the chain map?
Yeah, it's a complex.
Instead of changing D to 0.
D square is 0.
So if you change D to 2D, or 3D.
Yeah. These are equivalents. If I'm working over C, yeah, they're equivalent.
Yeah. So you're just saying that that's constant go to 0, then that becomes this greater map. Okay.
Yeah. But you see, in general, the D is you scale it. It doesn't change the isomorphic class, but you can deform the differential, right? Then you certainly can have a different. It's not just like deforming the vector bond. Also, the morphism can be deformed. Yeah, but the scale doesn't really change the isomorphic class. Yeah.
Well, just saying the map P is kind of look like you change like the extension class to 0 like that.
You mean the P map?
Yeah. Just scaling D all the way at the very last moment becomes 0, right? That's the map.
Right. So the P map just forget the information of the morphism.
Yeah.
But the Q map do remember D, but up to a coarser equivalence.
Okay. Okay.
Yeah. Okay. So our main theorem is the following. So PQ, you consider it as a map from a complex of C into the product C is a Lagrangian morphism with respect to the symplectic structure omega minus omega. Okay. So where omega is the one-shifted symplectic structure of PTVB. So remember, vector graded is a substack, open substack of perf C. Therefore, they're essentially the same. But here, this minus sign is for obvious reason. What I really says is this is the Lagrangian correspondence. Okay. So and in particular, so this theorem implies that after appropriate definition, so this complex C as a stack admits a zero-shifted Poisson structure in the sense of collect PTVB. So I don't want to define this term, okay, since I don't need to really use it. So what I really need is only the classical shadow. So again, I'm going to give you some idea. How do you use the PTVB Poisson shifted Poisson symplectic structure to produce a bivector? Okay, so let now V be a object in this stack, i.e. it's a bounded complex of vector bundles. Okay, so V will be something like VI plus 1, bounded. Okay, so the tangent complex, okay, actually after a shift of the stack at this point is precisely the hypercohomology I should really say it's cohomology of the tangent complex is really the hypercohomology of the upper half of the endomorphism complex of V. So remember, endomorphism complex, you have to allow any maps of any degree from Vi to Vj. Okay, by upper half or bigger or equal to 0 means I only allow the map to increase the index, the homological degree. Okay, so and similarly we have the cotangent space. Again, it should be cohomology of cotangent space is actually the hypercohomology of the lower half of the endomorphism complex. Okay, so there are two differential involved, right? So because taking the cohomology of complex, you have two differential. One is the internal differential of the complexes, and there is another differential coming from the Czech differential. If you use the Czech model, but if you use the other model, there's also a differential associated to the complex when you compute the cohomology of sheaves. Okay. Okay. So in this case, actually, the bivector pi, which should be a map from omega v to TV, right? So is indeed induced by the following chain map. So I write, and remember, for the tangent, this is the upper half. So it's the lowest one is end0, and then you have end1, and then you have end2, and so on. Okay, so it's bounded because V itself is bounded. And for omega, you start with rightmost one end0 and end -1 and end -2 and so on. Okay, so the map is from omega to t, and there is an internal differential. So coming from the bracket of the differential d, so you have partial here, and for the lower half, it's dual. So the map is exactly given by partial dual here. It's easy to check. Actually, this map will be a chain map, right? So the only thing you need to check is this composition is equal to 0. Okay, so this is 0. Okay, so this chain map induce in the cohomology level the bivector that we want. Okay, but this should be really a result rather than a definition. So there is a definition of this Lagrangian morphism, but it turns out that this zero shifted Poisson structure give you exactly this bivector. Okay, so this is really a consequence. Okay, so and when you do the calculations, say on the cohomology level, like if you want to check the Jacobi identity, whatever, you should use this pi, right? And then you do some hypercohomology calculations to check the Jacobi identity. In practice, we're using this pi. Okay, okay. So this is some kind of remark about this zero shifted Poisson structure. So what is good about this is the following corollary. So if I fix some finite index set S, okay, so this is a
subset. Can I ask a quick question?
Yes.
So if you restrict to the vector bundle, it's just not greater, just one piece. Then
yes,
this is 0, right? The
yes,
Poisson
it doesn't give you
structure
anything. It doesn't give you anything interesting because on the vector bundle you have a symplectic structure, which is one shifted.
Yeah. Okay.
Yeah. Okay. So if you take a finite subset of set of integers, then I denote the vector S to be those graded vector bundle, so that Vi is not equal to 0 unless I belong to S. Okay. V is equal to 0 unless, sorry. Is equal to 0 unless I is in S. Okay. So, and then we have the projection map from complex C to vector S, right? So it just means you only remember those vector bundle in the index sets S. Okay. So then the conclusion is the fiber of the map PS cross Q and the map from complex SC to vector S bar. So here S bar means complement. are zero shifted Poisson substacks. Okay, so that means by taking the fiber, okay, so what are these maps? This map really means I either fix some vector bundles or fix the rest vector bundles and the quasi-isomorphic class. These conditions are Poisson. Okay, so this is exactly what this theorem says. They are Poisson substacks. Okay, so you may wonder why I need these things. Okay, so now let me give some concrete example, and you see how this condition appear. Okay, so let C to be a simple vector bundle on C. Okay, say of rank K and degree n. Okay, so then I introduce a stack which is called n C, which are parameterize this two-term complex. Okay. So where this lower index correspond to the rank and degree. So V is a vector bundle of rank K plus 1 and the degree n, such that the quotient is isomorphic to C. Okay. So such modular space are not new. So for example, originally considered by Leportier called coherent systems. Okay. So this is an easy way to make modular space like kill the automorphism modular space by adding subsections. Okay, so right, so this is one example of this kind of fiber product. So let me explain. So I can write this as a fiber product by taking the fiber. To be at say 0 at O and C. Okay, what does that mean? So remember, in my definition, I need to fix a index. So here I just fix 0. Okay, so I want the 0 position to be O, which is fixed, right? And I want the quotient to be C, which means I want it to be quasi-isomorphic to C. Okay, so that means I fix like the Q map image. Okay, and then I take the fiber product. Okay, take the fiber product. Okay. So n C with the correct derived structure, it can be identified with the fiber product, homotopy fiber product of this map, right? So therefore it is fit into the example, the satisfy the condition of the previous theorem, and therefore it admits a zero shifted Poisson structure. Okay, so this make this zero shifted Poisson. Okay, but this space is actually fairly simple, right? Because n C, because I'm assuming C is simple, therefore it has the modularized, the coarse modularized space of that is simply just a projective space. It's the projectivization of x1, right? So i.e. abstractly is Pm minus 1. Okay, but the underlying Poisson structure that we obtain this way, okay, is indeed a quadratic Poisson structure. I.e. it fit into the example in the very first few slides. It's actually, if you can do some calculation to compute the bracket, it is of this form. Okay, but of course it doesn't look like that. Okay, but somehow if you do the calculation to really compute, translate from the bivector to Poisson bracket locally, you get this is exactly give you a certain quadratic Poisson algebra structure. Okay, so this kind of moduli space can be specialized to. It actually generalizes many interesting examples in the theory of integral systems. For example, if C is elliptic, then this moduli space will give you the semi-classical limit of so-called Fagan-Podesky elliptic algebra. Okay. So this, of course, can be further specialized if you take, for example, C to be line bundle, then it's a so-called generalized Kleinian algebra. And also you can take C to be the Kodaira En type or In type. Then this gives you the semi-classical limits of so-called quantum matrix algebra in the sense of Brown and the Goodyear. So that you can take other curves and you get many, many interesting Poisson manifolds appearing in the representation theory and the Lie theory. Okay, so these are just a few examples. Okay, so any question about this example? So the space itself is relatively trivial, but the Poisson structure is definitely non-trivial. You will see that these all have like infinitely many symplectic leaves. They're symplectic geometrically, they are very complicated objects. Okay, so the next example is even in the space level is not trivial. So let me now fix a line bundle on C of degree 3. Okay, so also I fix some point in the Jacobian. So now I want to assume for simplicity, I assume the curve is irreducible. Okay, so otherwise the Jacobian will become a little bit complicated. Okay, so now I consider a moduli space, which I called Mn L eta. But it turns out that the L doesn't really play a role in the definition. Okay, so well it does, but the Poisson structure does not depend. Okay, so this parameterizes such complexes, which is L dual tensor with a vector space Cn, map injectively to structure sheaf tensor vector space dimension 2n+1, and surjectory map to L eta. So here L eta means you pull back by eta. Okay. Tensor Cn. Okay. So I put further condition that BA is equal to 0. Okay, so this is a complex. Okay, so now you see that this moduli space can be also written as a fiber product, which is you take the point to be, okay, so here grade is C, perf C, and the point that you want to take is really L dual N O to n+1, and yes, take these points, L eta N. So that means you fix this each vector bundles up to isomorphism, and then I take the fiber product. So this moduli space is just constructed as a fiber product. Okay. Okay. So now I want to comment that indeed this stack is quite big. To simplify it, actually you can use some GIT construction. Then it will have a component, open and closed. Okay. What I denote by Mn eta semi-stable. Okay. So this one will have coarse moduli space. When you choose appropriate, sorry, here this one you need to choose appropriate character. So this one will have a coarse moduli space equal to P2 n. Okay, so here equal means diffeomorphic. So one component or semi-stable component will be diffeomorphic to the Hilbert scheme of n points on P2. Okay. However, note that in general, you do not have the same complex structure. You do not have the same Poisson structure. Okay, so let's just recall that I did give this example about, yes, you see, if I choose a anticanonical section, then P2 n, so here take S to be P2, then this does admit a natural Poisson structure, okay? But now note that I have a parameter here, which is eta, okay? So indeed, this is a Poisson deformation. And when eta equal to 1, okay, then this is exactly the Poisson structure and the complex structure on the usual Hilbert scheme of endpoints, which given by the omega inverse vanishing locus is equal to C. So that's the Poisson structure I put there. Okay. Okay, so this is already new. Okay, so before we don't know this space. So we actually, in this way, we construct Poisson deformation of this moduli space, the Hilbert scheme points. Okay, so let me just comment that if C is an elliptic curve, then again, this is known. This space is due to, these are actually the Hilbert scheme, the Hilbert scheme of some non-commutative surface of the three-dimensional Sgliani algebras. Okay, so this is due to Nevin's Stafford. So they first discovered this a modular interpretation of these deformations as also as a moduli space, but on something which is a three-dimensional regular algebra deforming the usual projective space. Okay, so but in general, you can take other curves and you get a bunch of interesting Poisson deformations, right? So they are, you don't have to take elliptic curve. You can take any Gorenstein-Calabi-Yau curve, irreducible at least. Okay? Okay, so this is the second example. Now let me, I think I'm almost out of time. So let X be a point in this stack of graded vector bundle and Y be a point in curve of C. Okay, so there be stacky points. Okay, so by stacky, I mean I consider the residue germ. I take into consideration of the automorphism. Okay, so then we have P inverse of X intersect with Q inverse of Y. So here intersect means in the derived sense, in the fiber product, okay, are zero shifted symplectic. Okay, so this theorem tells us that indeed we can foliate. Yeah, so this gives the derived symplectic leaves of the stack complex, because you can take all points, stacky points, then you get the foliation. Okay. But it's in the derived sense because usually this fiber product is a stack, and in order to get a ordinary symplectic foliation, you need to remove the stack case and also the derived stuff. And this usually involves some works, but in all example that we know, one are able to do that. Okay. Okay. So so this theorem has many applications in classical Poisson geometry and integral systems. When you want to classify symplectic leaves, let me just give one or two examples. Okay. So again, I take L to be degree 3. So the first one is relatively trivial. I take also C to be elliptic. Okay. So and then I consider the moduli space of extensions. Okay. So it's here V is a rank 2 bundle of degree 3. Okay. So such that the quotient is L. Okay. So and then we note that there are actually exactly 2 types of leaves. So the discrete invariant is just 2 choices. So first one, if V is stable, then such moduli space give you a 2-dimensional leaves, which geometrically correspond to P2 without elliptic. Okay. So clearly V is unique because the determinant of V is fixed. Okay. So the second type of leaf is when L1, when V is splits to a degree 1 line bundle and degree 2 line bundles. Okay. So in this case, Li are line bundle of degree I. So in this case, again, for determinant reasons, so we have L1 tensor L2 must be equal to L. Okay. So and then in this case, if we classify all such complexes, this is unique. Okay. So if you want the quotient to be L, so this is if L1, L2 are fixed. So this is in 1-to-1 corresponding with a 0-dimensional leaf, which is a point in C. So why there's a different point? Because you can change the one of the factors, L1, right? So you can tensor a degree 0 line bundle, but the other one is fixed because the determinant is fixed. So this tells you that in this example, the discrete invariants are precisely rank. So we have rank 2 and rank 0, right? And the continuous invariant, on the other hand, you see exactly is the isomorphic type of the split vector bundles. Okay. So in other words, we actually identify the moduli space of leaves with certain substack of vector bundle stack. Okay, so let me give a less trivial example when C is singular. Okay, so in general, you can take any degree 3 line bundles. You will have a 2-dimensional leaf, which is a complement of the curve, and that's a trivial part. But you see that when the curve is singular, then the singularity of the curve and the smooth point of the curve should not be the same discrete type. Okay, you will not be able to see that just from the purely Poisson geometry point of view. But now, if you have the moduli space, you will be able to distinguish them. Okay, so let me just give one example. I take this C to be a curve of En type. Okay, so that means something like this. So it's an affine chain. So in this case, again, I take the degree of the line bundle. In this case, it's a multi-degree. So it's 1, 1, all component 1. Okay. Because the line bundle restrict to each component is also a line bundle, and I want the degree to be 1 always. Okay. So then it's by a calculation, you realize that the number of discrete types or types. So now remember, I am classifying such extensions. Okay. Such extension. So this is a rank 2 degree n. Okay. And determinant is equal to L. Okay. So number of type of discrete invariants now is much bigger. So if you use rank, you should also get the 2, right? Either rank 0 or rank 2. But now in this case, you find that the number of discrete invariant type is actually equal to 2 to the n minus 1. It's a very large number. Okay. So, but for each discrete type, you're going to get a moduli space, and you foliate the whole moduli space, the whole Pn, right? So as some kind of symplectic leaves, but not symplectic leaf. I should put the twiddle here. So why it's not a symplectic leaf? Because you see that this discrete invariant, if it's fixed, you do not have symplectic leaf, one symplectic leaf. You have a moduli space of symplectic leaf, right? So this is really the so-called T leaves in the representation series. So because in this case, you have a torus action, somehow the torus action give you a orbit. Yeah, you act on a leaf, you get another leaf, but you form certain locally closed subscripts, right? So in this case, you see that using this vector bundle, so how do we get this number? This is really related to the classification of rank 2 bundles on En. Okay. Okay. So I think I will stop here.
All right, thank you. Any questions? Let me ask you a quick question. So if the curve C, just 1 second. Sorry. So if the curve C is the zero set of a anti-canonical divisor in a Del Peso surface, like before, right? I mean, because you're talking Del Peso surface, so are these two things related?
Which two things?
Well, so you have you start with a Del Peso surface, you have a Poisson structure there, which is a right. Now the zero set of the Poisson structure is what is one of these C, right? It's the Grothendieck-RBL curve.
Yes.
And now you have all these things on this C, and then the Del Peso surface itself has some Poisson thing, and then you can look at this power, and then another Poisson thing. Are these two things related?
They're the same, right? It's our theorem. So you see, the point is, yeah, maybe this is a point I should have explained, but I didn't. So if you look at this, okay, so this is a three-step complex on C, but this is nothing.
Where's the Del Peso surface? Where's the Del Peso surface? Yeah,
this complex is nothing but just the monad restrict to anti-canonical divisor.
Say again, where's the Del Peso surface? Yeah.
Well, you have a Del Peso surface, you have an anti-canonical divisor, You have
the
stable sheaf can be constructed as a monad, right? So which is a in the P2 case, it's a 3-step complex on S.
Yes, in the P2 case, but how about in other case?
But in other cases, just you have a longer complex. But always it's a complex of multiple steps. You can always do that. And then you can restrict that complex to C. And this restriction is a equivalence of stacks. Okay, but the moduli space, this restriction give you the Poisson structure using our theorem, and these two Poisson structure are actually the same.
So one of the Poisson structure is you're thinking about as the moduli space of like some bundle over the del Peso surface.
Yes, yes. These are the same. This is give you the same Poisson structure. You can either treat it as a bundles or sheaves on S, or you first use the monad construction and restrict it. And this restriction is actually a stack equivalence. And then you treat it as a complex on curve on the anti-canonical class, you get another Poisson structure. These two Poisson structures are actually the same. This is in our first paper proved. So it's just a unified way to construct this Mukai Botasin type Poisson structure and those Poisson structures. So those Poisson structures essentially are determined only by the curve. It doesn't use anything beyond the anti-canonical divisor. So it's really something should be understood using curve. It's more natural to view it as a curve because you see the point is you will not see this deformation parameter by viewing it as a moduli space on S, but you do see the deformation if you restrict to C.
How about you deform the del Peso surfaces, but not by fixing the curve itself, but moving the del Peso surface?
Well, when you move the curve, then when you deform the surface, I don't know if what do you do with the curve? You have to deform at the same time, or
no, you fix the curve, but deform the surface.
I mean, I don't know how is that done? I mean, so somehow is it possible to always do that, to fix the curve?
Well, so in fact, if you fix the elliptic, let's say smooth elliptic curve, let's say fix the elliptic curve, how many ways that you can realize it? And I can know curve with the Peso surface is the same as the moduli space of the EN bundle over the curve.
But that's local, right? But globally,
no, global. That's global.
I mean, as I said, I really think the Poisson deformation of the moduli space of vector bundle on surface has nothing to do with the del Peso surface itself. I think the only deformation should come in from the elliptic moduli. If you do that, for example,
but just say if you look at different del Peso surface, then all these are the same.
I think as long as first, it's not only about the del Peso surface. The Poisson structure depends on a choice of anti-canonical divisor.
Sure. There's a pair.
But as long as the anti-canonical divisor are the same elliptic curve, I think the Poisson structure will be the same. Yeah, Poisson structure will be, because it's just by this proof. Just by this proof, because when you restrict it, you will be able to relate the restricted moduli space on curves. See, that's actually the reason. So for P2, for example, it doesn't have any complex deformations, right? But it still have a Poisson deformation because the elliptic curve have deformation, even though P2 does not have any complex deformation.
It would be interesting to see how let's say you look at the del Peso surface of degree N, degree D, it's related to the Lie group En, where N is 9 minus D. Whether that come in now. Then.
You mean del Peso or elliptic surface?
Del Peso.
You're talking about below 9 points or?
No, below up to 8 points,
8 points, okay.
Yeah.
You want to see what? You want to see?
So one of the thing is what I just said, is that if you look at a fixed Grotstein-Calabi-Yau curve, let's say a smooth elliptic curve, fix the elliptic curve, the moduli space of EN bundle is isomorphic to the space of all del Peso surface of degree 9 minus N meaning D, which contain the elliptic curve as an anti-canonical curve. These two are the same moduli space.
What is EN bundle? What is? You mean the Lie algebra bundle?
Yeah. It's a flat bundle, flat EN bundle. It's a representation, if you like, of the fundamental group.
I don't know how does the Poisson structure depends on this bundle, it's
but you said that should not depend, right? Because the EM bundle is the same as the del Pesto surface containing that curve as the anti-canonical curve.
Yeah,
Fixing the anti-canonical curve, but moving the surface.
yeah, it shouldn't depend on. I think all the Poisson deformation of the, say, Hilbert scheme points on the Pesto surface should be able to realize.
But so what I'm saying is, because it does not depending on that, that may mean that you have further structure.
Oh, you mean coming from the Lie algebra structure?
Coming from the, if you vary the del Pesto surfaces, you may have some monodromy or some other thing.
Yeah, that's possible. Yeah, that's possible.
So if you look at fix a curve, and then if you look at vector bundle, so you can look at complex of bundle, right? As we are doing here. If you look at vector bundle E map to E tensor with some line bundle, but then you also assume that the bracket of those will be like a fixed. So this is like Hitchin moduli space type thing.
Yeah,
whether
so
you can realize it this way.
So first, the Poisson structure only exists when it's Calabi-Yau curve. So that's of course we use a Calabi-Yau curve. So we cannot take arbitrary Venus. But in this case, if you say on an elliptic curve, you take things like this, modular space like this. You're going to such modular space, you can get the Poisson structure will recover the R matrix.
But now you also need a phi bracket phi to be 0 condition, no?
So what do you need? You say it again.
Oh, that condition is automatic in one dimension. Okay, sorry, nothing.
Yeah. So in this case, this moduli space, you can take all D. You take the direct limit of all D. Then this is exactly this huge like in the scheme, like you take a m by m matrix with coefficient being the meromorphic function in C. So this is really the space if you take the direct limit. So this huge space has a Poisson structure using this so-called Darwin R matrix. And this is also one example of this modular space after taking the direct limit. So here I take V to be stable, rank N. Yeah. So this example appears in the Lie theory. So, but for the Hitching, I think you need to do things like a tensor with K, right? So and also the space is not the.
You don't have to tensor with K. If you tensor with other thing, you just get Poisson instead of Habakela.
Well, but that's not the same. So somehow in the Hitching moduli space, this Poisson is linear, while here the Poisson structure is quadratic. It's much more complicated the Poisson structure there. So I mean, somehow this PQ map exists for any algebraic curve. Actually, this is so-called theta stratification, if you want. I think it has been used by this moduli of curves people very often when they study the higher genus curve. But somehow in the elliptic curve case or the degeneration of elliptic curve case, this really have a symplectic geometric meaning, this stratification. That's somehow the point.
Very nice. Very good job. Any other question? Well, if not, let's thanks the speaker again.